Hello, my name is Nathan Hu.
I'm Josh An. Our lesson today will be going over improper integrals. So, we have this integral here. What's the answer or solution?
Well, it's a trick question, as it doesn't converge to any number. That is, the answer to this integral does not exist.
But not all improper integrals, such as this one, diverge.
For starters, an improper integral is an integral in which the limit of one of the endpoints approaches either infinity or negative infinity, or reaches a specified real number. For example, the two integrals shown on screen are improper.
The top one has infinity as one of its bounds, and the bottom one has an asymptote at x equals 5.17265, meaning that the function does not exist there specifically. Obviously, we cannot plug in a non-existent value or infinite values to find a numeric solution, making these improper.
Before we get to the numerics, let's test your understanding of this concept. Of the four integrals shown on the screen, use the definition of an improper integral to determine which is improper. Pause the video now and check your knowledge. There were three of them, and here they are, shown on screen now and bordered in green. Now let's move on to the actual numerical problems that you'll encounter. First off, we have this. Integral of 3 to infinity for 3 over x squared, and the graph is shown at right. Actually, the basic process of tackling an improper integral is quite simple, and we can use any other techniques for evaluating integrals, such as u-sub, for example. Here, we won't need that, but we can start like we do with any other integral. We take out the integrand and find its antiderivative, as the second part of the fundamental theorem of calculus shows. The antiderivative of 3 over x squared is indeed negative 3 over x, and then we can plug in the bounds. So far, this is stuff that we should be familiar with up to this point. The new stuff starts here, after we have found where to plug everything in. In a normal integral, say we have the bounds 1 to 3. Here we would find the value of the antiderivative at 3 minus the antiderivative at 1. However, we can't do that here as one of our bounds is infinite. What we do here actually isn't that hard. Instead of directly plugging in the value, we take another variable. For us, we'll choose b, and we find the limit as b approaches that infinite value for the antiderivative. In other words, we find the limit of the antiderivative as it approaches our improper value. Then we go as we've always done. We take our limit minus the antiderivative's value at x equals 3, which is negative 1, since negative 3 over 3 is negative 1. In this case, the limit as b approaches infinity for negative 3 over b is 0. So we have 0 minus negative 1, which is equal to 1, and that is our answer.
Alright, second problem. Integral of 1 over 1 plus x squared for negative infinity to infinity. So, again, we start like we always do, by finding the antiderivative. Now, if you take a look at this integrand, it seems a bit special. We don't need to do fancy things here, as we can recognize that the antiderivative of this is just arctangent or inverse tangent. So, once we have that, we can go about our improper integral process. We have two infinite bounds, so we'll have two limits. We take the limit of arctangent as b approaches infinity, which is pi over 2, minus the limit of arctangent as b approaches negative infinity, which is negative pi over 2. That gives us pi over 2 minus negative pi over 2, which just becomes pi by basic arithmetic. And that indeed is the solution. If you need, take a moment to look over this worked out solution on the screen. Here's some more practice. If you're up to the challenge, try to work this one out yourself by pausing the video, using the techniques from earlier in the video. Just remember to use limits to infinity rather than just plugging values in. But the rest of the process for integrals remains the same. Let's check our work. The antiderivative of e to the x, of course, e to the x, as nothing changes. Then, we take the upper bound, 2, and plug it into the antiderivative and get e squared, minus the limit as b approaches negative infinity for e to the x, which amounts to 0. So, we have e squared minus 0, which gives us e squared. That, my friends, is the essence of improper integrals.
Now, all of our examples until now have indeed converged. However, as shown at the beginning, some improper integrals may diverge, as the one shown on the screen is. If the limit to the integral goes to negative or positive infinity or does not exist, it diverges. For example, in this problem, the limit does not exist and thus the integral diverges. We hope this video helped you and now you have a good grasp on improper integrals.
And make sure you smash that like button, subscribe to our YouTube channel, and ring that notification bell for more math help videos.